this is problem 119 of Neetcode 150. Edit distance. So in this problem, we're giving two words, and the two words will likely not be the same. So we're gonna have to do modifications on the word one and only on the word one, so we cannot touch word two. And we have basically an unlimited amount of modification we can bring on this word. We can insert another characters at any position. We can delete a character or we can replace a character. So if we take a look at the first example, like what kind of modification to word one should we do to have this equal to word two? Well, first we're gonna have to delete this K and we're gonna have to delete this S. So when we look at this on a surface level, it looks quite easy, like just remove two characters and yes, the output is gonna be two because we have to remove two characters. But the challenge is going to be to do this in quite an efficient time and space complexity. So about O times, big of M times N. So we are going to use a 2D dynamic programming solution for this. And I will show you the solution right here. So let's say our word one is cut and our word two is cat. So we can see right away that the answer should be one. But our code doesn't know that yet, so let's see how we're gonna actually code this. But first of all, there are a couple of things I want to clarify. Okay, so what we're gonna do is that we're initially gonna have our two pointers starting at each word, and we just want to see if both characters are matching. And if they're matching, what do we do? Well, technically, we're gonna have to move our pointers on both words, right? And what does this look like in a graph? Well, it looks like a diagonal shift like this. And now we can see that our U and our A are not the same. So there are a couple things we can do. First thing we can, we can delete this A to try to see if the next character is going to be the good one. And by doing so, what are we doing? Well, we're staying on that same U here, but we're moving one cell to the right like this. So we know that moving to the right is basically equal to a delete. And well, actually, in our example, we have to modify only the word one. So let's just say that for the sake of this example, the word two is going to be the vertical word because I just modified the horizontal one. It's not a big deal. It won't matter much. So okay, so we know that going to the right is deleting. Once we know this, what are the other options that are up to us? Well, um, instead of deleting, we can actually update the value. So we can basically switch the value A to be a U, and in this case, it will actually match the value of the vertical word. So with that being said, what we can do once these two are matching, then we can just move our pointers again by one, and this will result in a diagonal shift, right? So diagonal shift is a replace. Great. Now what are our all the other option? It's basically to add. So what if instead of deleting A or updating A, we actually add a U here that is like between the C and the A. So then instead of going directly to this A, we're gonna go to this U, and now both are gonna be matching. So then we're gonna go move our pointer. So the U of the vertical word is gonna go to the T, and the T is gonna point to this A. So what this is gonna look like in the graph, we're just gonna go down. So we know that going down, it's gonna be adding. So these are the three operations we can do in our graph. And now you have an idea of what this looks like. And now there's another point I want to mention before I jump into a more concrete example. It's that if I'm starting from, let's say, this position here, what will be the value in this cell? Because each cell is basically going to represent like how many operations we're going to have to do at this particular place until the end to basically get the correct word. Well, if we're here, we're starting with our full word two, right? Because we're starting basically at the C value of the cut word, but we're starting from an out of bound index um, of the word cat, which is basically an empty string. So this is basically saying from an empty string, how many modifications do I need to do to reach cut? Well, it's going to be three, right? Because I'm going to have to add the three characters of cut. And same thing is going to apply here. If I start at this position, I still have an empty string on my horizontal word, but now I have a UT, which is two characters. So I'll let you guess how many characters will be needed here. It's going to be two. We're going to have to add two characters. Here it's going to be one, and here it's going to be zero. And same thing for the horizontal last row. Um, we're going to have a 3 here, a 2 1, and a 1 here. And to solve this problem, we're going to use a bottom-up approach. So we're initially going to start at this cell. And what we're going to do, so we're going to check if both characters are the same. If they are the same, like it appears to be in this case, both T are, well, the same characters. What we're going to do is we're just going to go retrieve the character that is diagonally down to this. And this is going to be set to this case. So its value is going to be set here. And now we're going to move. So we're going to go to the left. We're going to go see this particular cell. And what we're going to check is T the same as A? And if they are not the same, I just want to go see my three other options. So notice that if I go to the right, I see like how many characters, how many modifications I will need to complete this, the two words. So the two words are the same. So if I go to the right, I can see that by deleting the character right now, I will have basically zero additional modification. If I replace this character now, I will have one more modifications. And if I add a character now, I will have two more modifications to do. So what I want to do in this case is I just want to delete this character. So this is going to be one equation or one modification. And then for the rest of the string, I'm going to have zero modifications to do. So I'm going to do basically 1 plus the minimum of all these three values here, which is going to give me 1. And I do that whenever the character is not the same as the other strings characters. And this is also going to happen here. So the T is not the same as the A, as the C. So what I will do is that I will check all the operations that we can do from this position. Can I delete? Can I replace? Can I add? What is the minimum amount of moves that we're going to have to do for each of these options? Well, it appears that by deleting, I'm going to have to do one additional modifications to reach the completion of twice the same string. So with that being said, I will have to do one deletion here. So it's going to be one move plus this minimum value of 1. So I'm going to have a 2 in this cell. And now if I move here, I will be comparing U and T, and they are not the same. So once again, I will take a look at all the modifications, and it appears that down there, if I basically add a character now, I will then have no other modifications to bring to get W1 to equal W2. So I'm just going to add 1 here. So I'm going to have this modification, which is the add, which is one operation, plus the others, well, the smaller value between these three. So I'm going to add a 1 in here. And now we'll be comparing a U and A here. And they are not the same. So once again, I take a look at the three values here, and I can realize that by replacing a value here, I will have basically no extra modifications to bring after this replacement. So I will just do this replacement update, which is 1, which has the cost of 1, and I will add to this the smallest value between these three. So this is going to give me a 1 here. And to the left, we're going to be comparing a U and a C. They're not the same. So what we're going to do is we're going to just take the minimum value between these three and add 1 to this. This is going to give us 2. When we go here, we're going to be comparing T and C. And once again, we're basically going to take the smallest value, which appears to be the modifications of adding a value, which will brings us down with a case of 1. So this is going to give us 1 plus 1, 2. So we're going to put 2 in this cell. And to the left, we're going to have a C and an A. They're not the same. So once again, we're going to check for what is the move that will lead us to having the smallest amount of modification to bring afterwards. And it's going to be basically either adding or replacing. So it doesn't really matter in this case what we're choosing. We're just caring about a number. So this number is going to be 1, and we're going to add this modification here to it. So it's going to be 1 plus 1, 2. And finally, C and C are exactly the same. So if you remember what we're doing when we have exactly twice the same value, well, we're just going to pick the case that is diagonally down. Because when we have two values, remember, we're just moving our pointers. We're not doing any modifications. So when moving our pointers, basically going one cell diagonally down. So this is why we're going to have a value of 1. And now notice that this very first cell is going to tell us how many modifications we have to bring to the words 1 in order to make it equal to words 2. And this makes sense because from cat, you can just replace this A to a U, and boom, you have cut. So let's go ahead and write this in Python. So first of all, I will be willing to create two variables, m and n. And m is going to be equal to the len of word 1, and n is going to be the len of word 2, so that I don't always write len word 1 and len word 2 through my explications. And I want to create basically the grid that we spoke about. So initially I will set these to be equal to 0. So I will have a couple zeros here. And I will initially set my word, well, it doesn't really matter, but I will set my word 2 to be horizontal. So I will set basically n plus 1 length for a single row. And I want to have this for basically for the length of the word 1. So for range m plus 1. All right, so now I have a complete grid. And the next thing that I want to do is that I will be willing to set these side values. If you recall here, I had like a 3, a 2, and a 1, and it basically means that I want to take the index of the row. So this is index 0, this is index 1, this is index 2, and I want to take the len of that particular word, and I want to subtract that len, which is 3, minus the index, and that's gonna give me basically how many characters from an empty string do I need to add to get the rest of the words. So what I will do is that I will say for I in the range, and now the first thing I want to do, it's basically to go through every single row. So I will say for I in the range of m plus 1, and I will be willing to say that the dp at the index I, and I want to reach the last index or the last column inside each row. So I will set it basically to be the n every time, and this is going to be equal to the len of the word 1. So it's going to be m minus I, and I will do the same thing for the column. So I will say for g in the range of n plus 1, and what I will do is that I will always be willing to get the last row's value. So I will say dp at the row m, and I will set the column to be g, so I go through every single column, and this is going to be equal to n minus 1. or minus I, pardon me. And now we can jump into the um, the algorithm. So what we are basically going to be willing to do is bottom-up approach. So we're going to go basically starting at the last row up to the first row, and from the last column up to the first column. So we'll have two for loops. So we'll have for r in the range of m plus 1. All right. But actually, I want to have basically up. I want to have this in the range of m only, because I want to go in a reverse order. So this is what I'm gonna do. And I want to also start at the last index, so I will have my minus 1 here. And then I will do the same thing for the column, so for c in the range of n minus 1. All right, so now we're gonna start at the last cell, and we're gonna go up to the top left cell. And what I will do is that I will first check if the word 1, which is laid out vertically, so this at the index of the row, is this equal, and now I forgot my if statement, so if this is equal to word 2 at the index of the column, well, in this case, we are just going to set this value at this row and at this column to be equal to the value that is diagonally down. So it's going to be dp at row plus 1 and column plus 1. Otherwise, it means that we want to take the minimum value between the two operations that we have, which are delete, add, and replace. So I will set the dp at this row and at this column to be equal to 1 plus the minimum value between dp of row plus 1. So I will go see the cell that is to the right, the cell that is down, and the cell that is diagonally down. So it's going to be dp row plus 1 and dpc. Right, this is going to be basically deleting. Then I want to see dp at the same row but at the column plus 1, so this is going to be adding. And then finally I want to see dp row plus 1 and column plus 1, which is going to be updating a value. All right, and now I'm basically going to return the top left value, so at the index 0, 0. And this is going to give us the solution. So let's test this out. So we got a wrong answer. Let's see why. Oh, actually my error is quite dumb. So here I'm saying for G in the range, but I'm actually subtracting I instead of G. So this is why the initial setup failed, hence the answer fell. So let's test this out. And now it works. Awesome. So now let's speak about time and space complexity for this. Well, notice that this dp here is basically storing the row of the len of n, which is word 2, and it's storing these list for the range of m plus 1, which is the len of word 1. So basically we're going to have n times n space complexity inside our dp. That's going to be the space complexity big of m times n. And for the time complexity, well, we are going through every case. So we have a for loop in a for loop. So we're going to go see every single cell inside this dp. N's or time complexity is also going to be m times n. So big O of m times n for the time and the space complexity. With that being said, I hope you enjoyed the video, and I hope to see you in the next one.